Notacon.
This is my talk on writing exploits for war games. I make that caveat because in the wild you end up with a lot of things that I don't cover in this talk that you have to face. So you're not going to be able to take this and go root some server somewhere like right off the bat. Sorry if you were expecting it. Some of the topics I'm going to try to cover. The types of games out there for people who want to learn. This is the best way to do it that I know of. When I say learn, it's really about learning the programming skills and learning how the computer works at a very basic level. This isn't something that's going to, give you any kind of financial gain or anything like that. There aren't generally rewards offered for beating these games, but it is rewarding in its own way. It can be addictive in its own way. Types of exploits, the stack versus the heap and the difference between overflowing the two. There's actually some interesting little side effects of where your overflow exists, and it ends up being a lot about how you end up using it. Format string flaws, which are an interesting side effect of the way a particular function works. And a lot of the time when you see an exploit come out or a vulnerability come out, you'll see it in a function, or you'll see it as a usage that wasn't intended, something that the programmer put in as functionality, but can be easily turned into an attack vector by allowing you to write arbitrary data somewhere. And format string flaws is an excellent example of that. Sanity checking and such. One of the things that they've been trying to do lately is verify that what's supposed to be somewhere is what's there as best you can. So we'll take a look at some examples of that. And then arrays. There's a really basic, conceptual hack against arrays if you can control the index. So we'll just take a quick look at that. It's nothing interesting, but it is sort of applicable. Quick credits. Andrew Griffith, he wrote hack.datafort.net and vortex.labs. Wrote a lot of levels and a lot of the code that this sort of thing's based on. So Far, who's sitting right there, he's the man. Exort, he showed me a lot of the Malik stuff. It's really quite good. Also Dark Knight, he showed me a new way of doing some of the GDB foo. Was very cool. FRAC 2600 CCC, these organizations do offer opportunities for people to meet that should meet, I guess, and countless others who have contributed to the community over time. This is all material that has been out there for a long time. It's stuff that is in tons of text files, tons of intros to hacking. The thing is that they show you the sort of what you need to do, but if you don't have the basic, if you don't know what tools to pick up and what you need to learn, you're not going to get anywhere with it. So, war games. This is what this is all about. Hack.datafort.net, vortex.labs, and rootfoo by the Ghetto Hackers are three of the games. There's also games that deal with web authentication, stuff like that. That's not, NGSec. That's not my area. I don't know, but apparently it's well respected. Those are obviously vulnerabilities, need to be hacked. But we're talking specifically about C on Unix C systems and running arbitrary code. That's what these games are about. You have a binary SUID, meaning when you run it, you gain the privileges of the whatever user that binary is running as. So usually there's a simple challenge to get the login. As an example, on Vortex, it requires you to connect to a port, read in 4 unsigned integers, add them together, and then send back that sum. So it's a really simple piece of code that you can use Netcat to pipe around if you want, or you can write your own socket code and sort of, just make sure that you have some clue before you get on, because you do get a shell on the system. You usually log in as level 1 or something like that, gives you the password for that. And then somewhere, at least on Andrew's games, there is a password file. It's not encrypted, usually. It has just a hex string, which is the password for the next level. So the binary you have to actually exploit and get to run your code as the privileges of the next level that it's SUID to. Then with those privileges, you read the password file and you log in as the next level. And you proceed through the game this way, and there's usually a place to put your tag so you can write and go ahead and show, hey, I did it. Usually Unix system, and the web authentication challenges, no idea. There's also hacker games. Hacker games are a lot of different kinds of challenges. They usually have more of a GUI interface. You usually don't get a shell. And there's some interesting stuff out there. Arcanum, for instance, had some really interesting questions that weren't really related specifically to exploiting anything, but were just little mind teasers and programming challenges. For instance, they would give you some random numbers and you have to add them together in a certain way, XORing, things like that. Hackers Lab is actually run by a Korean ex-computer security guy who said, we need a place where all these hackers can do what they do without fear of prosecution. So he set up Hackers Lab, and whatever, I don't know. They got a bunch of boxes. Ciphers, programming trivia, SQL injection. A lot of these things, one of the pet peeves I have is when I first started looking at these, it would be like you'd have to view the source, and in comments would be the password. So that's sort of my stereotype of some of these games, a lot of these games. This is C code exploitation on the x86 architecture under Linux. Thank you. This is not hacking, inspired by hacking. Some people would argue about that, but it really is formalized. There's no, this was designed for this, and now you're trying to get it to do this. This was written to be exploited, and now you got to exploit it. So there's techniques you apply. It's formulaic, largely. That's where people writing their own exploitable chunks of codes comes in, and that's what these games are about. These are written to be tricky to exploit and to have a cool, it's not a side effect. It's not simply looking down different values. It's really tricky to get some of these to run your code. So it's really quite interesting. Motivations, education, dissemination. People put these games up to be played so people will learn. And not many new people are playing them. And the people who are playing them are looking for answers and not looking for where you have to go to learn how you could figure this out just with your own skills. And people are hopping on IRC networks and saying, hey, how do I beat level 1 of, hack.datafort? And that's not the way to do it. Don't look for answers, look for the path. That's some quote from somewhere, but yeah, it's important. And there's similar educational opportunities. I dig programs like Model UN, Odyssey of the Mind. I believe that they're excellent and good opportunities to learn and grow. That's my little thing. Yeah, so stack and heap overflows, format string flaws, running shellcode versus forcing behavior. Sometimes you can get a program to give you what you need without actually going to the level of forcing it to run arbitrary code, just as a side effect of how it runs. That's another side of it. It's right on, but it's not quite what I'm covering. So we're running shellcode. Malloc and linked lists. Malloc, we'll get into that near the end. The stack and heap. The stack is where, when a program runs, you start with an execution pointer, and that's where the code is going to be run. When a function is entered, it pushes onto the stack an execution pointer for itself. And then on another stack, it'll push, whatever variables it needs, whatever arguments. That's very, stripped down. And then, as it runs, it'll pop itself off, and then if it enters another function, it'll push onto the stack. So what we're trying to do is get the function to copy our address to EIP, which is the execution pointer, or we're trying to get it to, we can do that with a direct overwrite, we can do that with any number of things. Or we're getting it to try to call a function which will then, for some reason, because of arguments we've corrupted, then call EIP. So we don't have to do it immediately. At the point of the overflow, we don't necessarily immediately overwrite EIP, we don't immediately hijack. We can let a few instructions go, and then somewhere down the road, we'll end up hijacking EIP. The heap, on the other hand, is where the static stuff goes. If you statically define something in your C file, it will be on the heap if you specify a size. And the stack is for things that end up getting allocated along the way. One of the caveats to that, malloc, which does sort of dynamic memory, gets on the heap. But the reason is because you always specify a size. So it can go on the heap, no problems. Heap gets copied to stack all the time. So stack contains EIP. When function is entered, it's pushed. When function exits, it's popped. Overwrite EIP, next code executed yours. Detours. There's sections of the actual file that get loaded into memory, and some of these sections are predetermined by the ELF standard, which is the binary standard, to be run at certain times, like the end of execution. You provide convenient locations to overwrite, to enter a function, or enter what it thinks is a function, but is actually your chunk of code anywhere, pretty much anywhere in memory, unless you're talking about some protection schemes. Unix stuff. All right, so since we're talking about Unix systems and not everybody might know it, I'm just going to cover this real quick. Unix has multiple users. They're each identified by a unique ID, which is a number. SUID binaries means that when it launches, every program running is owned by a user. It's attached to a user ID. That's what determines what privileges it has on the system when that program tries to access a file. Because you as a user never access anything. The programs you call access things. So they determine their privileges from who they were launched by. In this case, it would have been the whoever originally launched the executable. SUID binaries, on the other hand, when they launch, they have the privileges of whoever they're SUID to. So you end up being able to have the privileges of the user who launched as. I think that's clear enough. There's streams connecting. There's three basic streams. One to your screen, one in from your keyboard, and one to your screen that's an error. That's just for errors. Okay, that's pretty much it. You can create streams. There's a lot of stuff going on there. Shells are what connect those streams to your I/O stuff. So they're what allow you to interface with the system. So if we can get our shellcode to launch a shell as the UID of the next level, then it's as if we were suddenly that person. So we go from being able to launch whatever code we want to being able to interact with the system as a user, as that user. So it takes it to an applicable level. Yeah, shellcode is custom code often meant to connect streams and launch shells and things like that. Sometimes there's, for instance, what if the binary closes all the streams before it launches your code? Well, you have to have a chunk of custom shellcode that just calls whatever you need done to get access at a later point, whether that be add a user, copy the password to a temporary file, and change permissions on that file so that your user ID that you have at lower level can read that file, and then you can log in. And that does happen. That is a common thing to see in some of these games also, and that requires Unix knowledge to beat. A lot of this stuff you just can't. There are no answers for it. I mean, there are tons of them, but you're not going to sit here. Nobody's going to sit there and tell you all of them because it's just too much stuff. Learn Unix, and you'll be able to get some of that more advanced things. Some C functions copy memory from one place to another. It's actually the assembly that does that, but we're thinking at the level of C right now because it's a little bit easier. When the function copies too much, the computer has no way of knowing, unless you tell it, what size the place you're supposed to be copying to is. unless it's like a string and it's null terminated and things like that. But in general, what it does is it will cast. So it knows that if you declare an unsigned int, it'll take so much space, that sort of thing. But when you start talking about strings, the size will be defined as, say, 200 bytes. It's called a static buffer. It means it takes up so much space in memory, period. If you overwrite it, you overwrite variables, you overwrite heap, you overwrite stack, you overwrite all kinds of fun things. So let's say this first part of the stack, each of those different colors is a different thing in memory, all right? And very basically, this is where whatever this is used to be. And we overwrote it. So if that's used by a function, that means we can alter the way the function works. We can force it to do something that it wasn't going to do that we're interested in doing. And then obviously, you can also overlay P. Either of these and any number of other options will result in foreign code. So. Each address can only have one value stored at it. So if we overwrite an address, at the value stored in an address, at a pointer, then that value will change. The old value will be gone. This is, you know, when you see program crashes in C programs, it is often this. It is often crashing because it's really hard to keep track of what's actually happening in memory. There aren't good tools for viewing step by step, you know, what the memory looks like and colorizing it, you know, things like this. With new GUI stuff, that would be incredibly useful, but it's not really out there. Here's the code I'm going to be using. Yay, code. This is just making sure we have an argument. And then it calls the function vulnerable. Vulnerable is defined here. We define a static buffer. And then we use an sprintf. The reason we're using an sprintf is because we can combine nice, good old buffer overflow and format strings. Yeah. In front of a buff, because I'm copying to the address, to the actual pointer to, I don't know. Yeah, well, the pointer would be to the first address to buff 0, so that should be fine. So right here, what we're doing is Perl is really helpful for sticking shit into a program because you can print hex. So I'm printing 1,000 A's. Print A times 1,000. 41 is the ASCII code in hex for an A. So if I overwrote those with capital B's, that would be 0x42424242. What this means is that there was a jump to a point that I overwrote, or you know, any number of potentialities. Since I statically defined that buffer, I probably overwrite heap, so I could have overwritten you know, a function pointer or something along those lines. But we'll take a look at what actually happened in a second. So now that we control that jump point, we can overwrite that with the address of our shellcode. I'm storing it in an environment variable. The reason is anytime you launch an executable, Linux x86, blah, 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 you inherit the environment from the parent, which makes it really convenient because since screen is the parent of the process I'm launching, I can keep the same environment time after time, so I don't have to worry about if I log in from somewhere different, this code isn't going to work right because I don't use an off sled, just for accuracy's sake. Environment variables can be found in the heap near the EBP pointer. We'll take a little look at that later for actual seeing where that is and how to look at it. x86 is little Indian. Endianness, there's another entire class of exploits, what's called a sort of, they're flaws where the endianness, which means how it's stored in memory, either backwards or forwards. So it's by word. So DEAD would be AD and then DE. The bytes, which are 2 hex digits, are together, but well, each byte is reversed in the word, and a word is 4 bytes in an x86 system. So, or well, like I said, Linux. And you overwrite that with the function pointer. So what I'm doing here, I'm printing these hex characters, which is Aleph 1's code from smashing the stack for fun and profit to a temporary file, and then I'm running this line, which is actually redundant. I could have removed this entire section here and just moved this back. I think I actually did that on the system, to cat that into an environment variable, and then I run my GDB string I've prepared here. So that's when we jump into GDB. You usually want to put that in the environment before you launch GDB, so that any processes launched by GDB will have it in the environment. All right, so this, for instance, let's see here. Let's see what we got. Sure, yeah. All right, so the actual line I use here it's just run A times 5,000, and we end up with the seg fault here. The way you would actually do this without using these command files, what you see, these last 2 lines, run perl-e, that's what you would type directly into GDB. So you would type GDB, name the executable, and then you would type that line. For those of you who are sort of Unixy, these backticks, anything inside of backticks will be executed, and then whatever was returned by the program will be inside those backticks. You can think of those being replaced. So that will perl-e runs from whatever's on the line rather than what's in a file. That doesn't mean you can't put a file in your home directory and just do tilde/ and then your Perl file or whatever you want to do. So let's okay. This is real straightforward. Basically, I wrote enough A's to override my buffer, and I jumped to a shell here. When you actually do this, since you're doing a jump out of the code, you end up with a sig trap. So don't freak out when you see that. Don't think, oh crap, and Control-C and start over. You're good. You're there. So let me show you what that line looks like. All right, so first off, we're doing the shellcode thing again. This is the exact same thing as last time, prepping the environment the same way. We don't actually have to do this a second time because it's going to stay in the environment. So if we were to do it inside of GDB and then exit GDB, it would not be in the environment because GDB is not the parent of our bash shell. Bash shell is parent of GDB. So we stick it in GDB in the bash shell, and it will be there for GDB every time we launch it from that shell. And then here we see actually the resolution's high, the size is high enough I wasn't able to see this, but I printed this 4.1 here in this one just to show that it said segfault at 4.1 FF F313. When you see that 4.1, 4.1, 4.1, 4.1, the most intuitive way to start actually exploiting it is to start deleting A's one by one or by in groups. The correct way to do it is to look in memory and find what your offset is, find what you're overwriting, figure out why it ends up in the IP. You don't have to. You won't learn much, but you can do it sort of ghetto style and just start deleting stuff and start throwing B's and C's and D's and stuff in there, and you will see the different values show up in the point that you segfault at. So that was just an example line. This is the actual BFFF351 is the address of egg in our environment variables. And we jump to that address, and we get a shell. Format strings. Printf is a function meant to make text pretty for the console. This string right here will print hello, a space, and that percent, unless it's a double percent, will get read as something special is going on here. So %s, and then it'll print this, Sam, instead of that %s. So what you'll end up with the line is, hello, Sam. Here we define a buffer, a character array, and we stick Sam in there. And then we call the same thing with the name of the character array instead of putting it in the quotes. Doesn't care, it sees it as a null terminated string, and it uses it. There's actually something interesting for those of you. Since a string is null terminated, if you can overwrite the null termination at the end of the string, it will continue until it sees another null. And that is a trick you can use sometimes to, when you have limited options for trashing memory, you end up finding little things that let you get away with stuff. And normally, the programmer supplies format strings. User supplies input that is inserted into the string by the programmer. What we're looking for is when this happens. The 08 specifies that we're printing 8 hex digits, because the X stands for a hex digit. And we're printing the address that buff is stored at. Wrong way to do it is printf buff. The reason is, if we have a %s in buff, then it will print whatever string it thinks is pointed to by printf. Whatever I should clarify that a bit. Printf, when it enters, has its own little like stack, is the best way to think of it for its variables. And when it tries to print %s, for instance, it will go to whatever's next in the stack. But since we didn't enter printf using argv, which allows you to pass multiple arguments, the next thing on the stack could be anything. And eventually, it will be actually the format string itself. So, take advantage of this. %s prints a string. Signedness and endianness are the two things you need to consider when you're talking about intuitively changing C code into what it looks like in memory. And also a ton of crap about how it actually stores memory. So an unsigned decimal integer can only count up, and it can count up to about, what, like 4 billion or something crazy like that. It is literally 4 bytes, or no, yeah, well, I'm not going to try to figure it all out. 8 hex digits is 4 bytes is 1 word. x86 Linux. That's, for instance, a valid address. Bad coded. Yeah, you probably, well, BF. Yeah, that would land somewhere. That'd land somewhere. %n, on the other hand, unlike everything else that prints something or specifies formatting for something, nothing is printed. Number of characters written so far is written to whatever pointer is on top of the function stack. If you don't have the proper arguments pushed, as if we provided our own string rather than programmer providing the string, then whatever's on the stack, you can just keep pushing until something's on the stack that you like and that you want called. %n is the only modifier that writes, and there's that caveat one more time. Assuming you can provide the string, finding the offset means that we pop the stack so many times. Each of these pops a stack. Each of these %08x, because it pulls 8 hex digits, which is the same as 1 word, which is the same as 1 address, 1 pointer. So finding the offset means just doing enough pops, or using, there's another technique where you actually specify an offset. I'm not going to cover it, but it is the sexier way to do it, I guess. Only works on some OSs. Direct referencing of stack variables. So here, this is what this printed out. The brackets don't have anything to do with this format string. They actually get printed as brackets. What we end up here is A, that group of 4 A's, is printed out by that %08x. 8 prints 8 hex digits. The argument that it happens to pop is 4 A's. So we end up with 41, 41, 41, 41. Then we got B's, 42, 42, 42, 42. That's what we want to see. Now you are controlling what that format string is doing. Oh, right, finding detours. This is pretty important. Object dump will take an executable and print out its sections. One of those sections is detours. When you actually run this command line, you will end up with like 4 lines. One we're interested in is detour end. Here's an example where those A's were. I'm not going to print the hex characters I'm interested in writing backwards. 08, 04, 83, 48. I actually did these at different times, so never mind the fact that's not actually the address that it says we want to go to, but whatever. And what'll happen is this %n here will write this address, which was those A's, is now our hex address. We'll write to that address the number of characters we've written so far to the screen. So list in GDB will show you your code. List line number will show a specific, or centered around a specific line number. So if you do list 10, it'll show like 5 through 15 or something like that. If you have it like 20 lines large. So x/ will print whatever stored at the address you specify in GDB in the format that's specified by the second argument. So x means we're printing hex information, and since I specify a pointer, it prints out the pointer and what's stored at that pointer, actually. So we use break, and I usually use like break 1 and start stepping. When you use GCC, use the -G GDB flag to make GDB work with your executable. It's pretty important. And you'll end up, if you are at the right point, you'll end up with this line here. Also, you can use display /x $EIP, and each step it will show you what EIP is. So if you're really unsure, try writing to EIP each of those points. I mean, a lot of this stuff really comes down to how you want to solve the problem. There's no, there's right ways to do this, but you don't have to do it the right way. You can just do it for fun as a challenge. Just jump in, go for it. So for instance, this line here, it's not very clear. These are 2 pops so that I end up at the beginning of my format string. And then I'm doing 4 successive writes of a byte. So 48950. So here's the first place, the most significant byte that I want to write to, which would be 2b. The reason being it's 2b is because we printed these 2 brackets after the 29, which was written by the previous address, and then the 2725, and that's why it steps down 2b, 29, 2725. B is 11 in hex, 11, 9, 7, 5, 2 apart from each other. That accommodates for the brackets. So that's what's happening there. So our shell code is at BF, FF, F313. So we print this string, which writes to our address of detours, the value BF, FF, F313. The way we do this is I use these lines, which print so many A's, to go ahead and push this over. There's better ways to do this. There's way better ways to do this. You can use %.238 D, and it will print a decimal number with 238 points after the whatever that thing's called, a period point, whatever. Yeah. Decimal. It's called decimal. A decimal point. Yeah, there you go. And it'll print the number of characters you need, and not look so funky. But this is more intuitive. We're printing A's there, and it increases the number of characters written so far, so that %n is what we want it to write. So that's how we control what %n writes to the address that is on the stack, which is the beginning of our format string. Malloc and doubly linked lists. Many operations that copy data can be made to copy data to an arbitrary location. You can sort of read that. Once again, there's a lot of functions that do funny things. There's a lot of algorithms that, by nature, copy data around. If you can get in and corrupt that, let's say you don't have any convenient way to overwrite a point that gets jumped to, you don't have any convenient way to overwrite detours or EIP. There's other ways, for instance, format strings, to write to those addresses. So maybe you can only corrupt a bit. If that was for instance, luckily on x86, since it's a little endian, when you overwrite a bit, that is the bit from the least significant byte. So if it's a small number, you can decrease that number enough so that if it's an address, it suddenly falls short, and if it falls short of where it was, then it might end up where you control. So it is possible to do an exploit with 1 bit. A linked list is something that points from element to element in memory as a pointer to the next thing and a pointer to the previous thing. A doubly linked list does. When you delete one of these items, it has to copy the next pointer from the one you're deleting to the previous pointer plus the offset to the next in the struct, the address of next, and then it does the same thing with the previous address to next to the offset of the previous pointer in the next chunk. So any point where you can overwrite next and previous, it will do plenty of writes for you to where you want it to go. So this is sort of hard to read, but think of it this way. If that's 0, wherever we're starting, this is 4, 8, 12, 16. In hex, that would be 0, 4, 8, what would be CF? Yeah? So those are each parts of a struct. A struct is a collection of different kinds of variables into one thing. So in this particular instance, we have previous size, which is the size of the previous chunk in memory, size, which is the size of the current chunk in memory, previous, which is where previous is, and next, which is where shellcode is. Well, next is where the next chunk is. It puts a pointer to the next chunk. It takes a second. And then data, which is the data, what is stored in that element of the linked list. This is a sort of standalone example, since we copy to the pointer next to the point where the pointer next should be in previous. We write to we write the address of EIP minus 12. The reason being, when it does the write, it'll take the next pointer. When it writes, it'll take the address in previous and write to an offset of that to where it thinks next should be the address of our shellcode. So if it's 12, if it's 3 bytes before, no, if it's 12 bytes before EIP, that's in previous, the offset will be, the offset to next would be 12 bytes after that point, which would be EIP, and then we write previous there. So that's pretty straightforward. Here, let's say previous size, we can overwrite 1 bit. Well, if that's the least significant, part of the least significant byte, then we can change it to something lower in memory, and then we can do the same trick, except this isn't where one of our elements should have been. It might be the data segment of one of our elements, but it doesn't know that because it checked previous size. This only works in a couple situations. It depends on what the algorithm is doing that is doing your D-link on your format string. So it's just a couple different ways of looking at it. Stack protection, canary values. When you actually start talking about trying to do this against some of the more modern stuff, what people do is, since you're trashing memory, one thing you can logically do is stick a value next to each of those critical values in memory and check it immediately after every dangerous function. And this works pretty well, except that that random value has to be somewhere else in memory. So if you can gain control of that variable pointer, you can do that. If it jumps out, then you have to get really creative to get that right, or to get it to something it will accept. For instance, in glibc, one of the things it does, I should actually go back. Yeah, one of the things it will do is check before it does any operations, size and previous size, to make sure they're more than the minimum size of a allocated chunk, which is something like, I think, maybe 12 bytes or something like that, 24 bytes. And then it will check previous size and make sure that it matches what it thinks should be at previous, or it will take previous, use prev size as a, what's up? Oh, it'll use prev size as a sort of offset, and then make sure what it finds at the next location where it should be a pointer is a pointer. What's up? No. I have mainly read about canary values. I don't really try to defeat them. It's not required for the games usually. I know have the ghetto hackers done. executable as X, but not canary values. So this is something that would be interesting for games and effects if you want to write exploits, but I guess it really hasn't been done. Somebody will do it. Yeah. Read Frack. Frack will tell you all about it, and it's an excellent resource anyway. So, good stuff. Huh? It'll give you this error. I think I can actually make that error happen real quick, which is basically failed check. And it'll say which point of the check it failed. The beauty part is this is all open source, right? So you can take a look at what those checks are, and it'll check against things like AV, dereference system map, and things like that, which are values which are just logic values. All right, I know I have this much memory, and logically this program shouldn't take more than this much. So is it less than that, the size of this chunk that supposedly belongs to this program? It's really hard to get past this. The best guy I know at this kind of thing is this guy No Life on DARPA, and Gara's insecure programming challenges are a collection of like 60 exploitable chunks of code, including malloc stuff, double freeze, all that sort of thing. He wrote an exploit for ABO 9, Advanced Buffer Overflow 9, which is basically malloc, and it's really interesting. You can Google around for it, and it's good stuff. But anyway, I gotta get going here. Previously explored capable fitting in system memory. Is a valid address stored in an offset? You can tell pretty easily if you have a valid pointer. It should fall within, you know, some basic ranges. Arrays. All right, this is wrapping up here. X has a number of elements equal to Y. Okay, so the kind of element has to be defined. So if this is int X, then it has, in this case, 10 ints, which are a specific size. If it has 10 characters, it has 10 ints, which are a specific size. In this case, in C, providing an array index literally translates to an offset of the expected size of the element type multiplied by the array index we give it. So if it expects the element to be 4 bytes and you specify 3, then it will do 4 times 4 to figure out how many bytes your offset should be from the base pointer of the array. And the reason I say that is because x3, we start counting a 0. 0, 1, 2, 3. It's 4 elements. So if I write to offset more than 9, because we start from 0, that would be 10, really. You always have to consider that when doing array indexes. You can smash stuff. You can go anywhere you want in memory. What's really hard is figuring out what should be in memory and then recreating it, which is often necessary. Keeping stuff intact, big chunks intact, and then writing just where you want to create noise, and then a big chunk intact. It's really hard, and it's often necessary for one reason or another. This is just sort of, you know, being mean, but argc is how many arguments you have. So if argc is more than 0, exit, and then copy argv100 to a buffer. This is actually in a challenge. Just to give you an idea, like, well, I shouldn't really tell you this, but exec.le lets you specify an environment and variables and stuff. So there's a lot of different ways that you can make these exploits harder. That you can make them tricky to pull off. One of them is keeping memory intact, and you know, C Unix, at least a concept of ASM, assembly. And I would suggest GDB, GCC, strace is really cool. It shows you all of the system calls being made by the program. Fuzz will throw a bunch of noise at a program. I don't use it, but I'm sure it'd be helpful if you were really just barely getting into it and wanted to do something. Perl, you don't need to know much, Perl. And Frac. Frac is a resource, is an excellent resource. I'm going to plug them one more time. They're about to print their last, I guess, volume or article or magazine or zine. So go to their website before they die just so you can say you did. And my bibliography is Google. Seriously, this stuff is all very, 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 very public domain. It's just hard to learn on your own. It takes a lot of dedication. It takes a lot of sitting there and failing. These levels take months, sometimes, if you suck, to complete. You will complete them. You will eventually understand what's going on, even if it's not the way that you would normally look at a program and figure out what's going on. So keep at it. The rush you get when you beat it will be awesome. And it's good stuff, and you'll learn a ton about computers. A ton. So thank you. Any questions?
Coming in, did you know that you were in competition with Irish and myself? Not myself, but me, for the worst slides in
Did it win?
I think I was, but you got pictures. Yeah, but I give you. Pictures of his face.
Do we need to vote?
Sorry, I just wanted to see if you knew that you were in competition.
I didn't, actually. Yeah, they were informative. Come on. I don't like color. It scares me. Confuses. Any other questions? Not concerning the quality of my slides? Preferably. All right. Thank you very much. Let's wrap up.